Physics in Waterloo, Ontario, Canada. My name is Katie Mack, and I'm Perimeter's Hawking Chair in Cosmology and Science Communication. This week, Perimeter has been hosting its first ever SciComm Collider, a gathering of colleagues and friends in science communication, YouTubers, podcasters, authors, social media influencers, and other people who are passionate about sharing the wonders of science with the world. They're all here to learn from one another, be inspired, and dream up new ways to communicate physics and astronomy.
And hello, everyone. I'm Lauren Hayward, a teaching faculty member here at Perimeter. Perimeter Institute was created to be a place where people ask big questions about the universe. Perimeter is just over 2 decades old, but people on this land have been asking big questions about the universe for thousands of years. Looking at the night sky and understanding our place in the cosmos is a human constant throughout the ages. Perimeter is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples. The Institute is located on the Haldimand Tract. We are thankful to those who preceded us, and we are committed to acting responsibly and collaboratively to carry forward the quest for knowledge for the betterment of all. For those watching the live webcast, please join the conversation online. We are at Perimeter on Twitter, and Perimeter scientists are online to answer your questions. If you have a question for our speaker, you can ask it with the hashtag PILive, that's PILIVE.
Our guest speaker, Professor Stefan Alexander, began his journey to science in high school, where he encountered a teacher who believed in his potential and introduced him to the magic of jazz, fostering a connection between John Coltrane and Albert Einstein. He is now a professor at Brown University, studying cosmology, particle physics, and quantum gravity. He has been awarded the National Medal of Science from the nation of Trinidad and Tobago and is an APS Fellow. He has written 2 popular books, The Jazz of Physics and Fear of a Black Universe, An Outsider's Guide to the Future of Physics. Oh, and he wanted you to know that he wrote those books despite having received a C in freshman English. Tonight, accompanied by bassist Dennis Rondo, he'll take us on a musical journey of the mind, showing us parallels between deep cosmological puzzles and jazz improv.
And now, please join me together with Katie and the whole Perimeter community in welcoming Stefan Alexander.
Thank you. Okay. Well, I'm just so humbled to be here. I just remember back in the days when I was a postdoc, I used to come out here in the early days of PI and across the street from watching in the middle of winter, watching the hockey games with a nice pint. So it's good to be back and a great honor. So, what else I have to say? Thank you, PI. Thank you, Katie. I promised that I told Katie I promised I would do this unless she signed a copy of a book for my daughter. So you owe me a copy of that book. So let's begin, okay? Full disclosure. So today what we're gonna do is look at parallels between music with a focus on jazz music and my field of study, cosmology and particle physics. The important point here is that I'm doing analogies. We're making analogies. By no way am I trying to say that everything you're going to see here, that the universe is jazz or that the jazz is the universe. If you want to believe that now, be my guest, okay? I will not disclose what I believe. Okay, so let's begin. When I was, I think I'm just going to step out here, yeah. This is actually, I bought this little horn here because I can travel with this. It may look like a toy, but it's a Ferrari, okay? But this one here, yeah, I just lost my thing here. Okay, oh, it worked, yeah. So this is my Selma Mark 6. I was at the music store across the street. What's the name of that store? Yes, what's it called again? Yes, McQuaid, and yes, I was trying to rent a tenor. But I decided to just play my little horn here tonight. So when I was younger, I grew up, immigrated from Trinidad and Tobago to the Bronx when I was 8, and I grew up in a musical family. It was expected that I was to my grandmother wanted me to be a Broadway musician or something. She I'm going to pay for piano lessons so that you can go do that. But I hated practicing the piano. Then my father brought home a used saxophone, and it functioned more as a toy. So I didn't think that I had to practice this thing. And it stuck with me for the rest of my life. But the point there was that when I was growing up, I was very inquisitive like a lot of young people. And after reading all these comic books and seeing like a lot of these comic book superheroes and villains were once scientists, I thought that I might be a scientist. And I grew up kind of with this tension, or I don't know, conflict. Should I be a musician? Should I be a scientist? And that conflict has continued throughout my life. And so what you're seeing and witnessing here is the conflict in front of you. And what you do to resolve a conflict is that you write books about it, and you give public talks, and you bore your friends with this stuff, So that's what I'm going to do today, okay? So let's move on. But the truth of the matter is, I'm a kid of the 80s in the Bronx. That's where hip-hop music was being developed, and some of my friends went on to become pretty famous people. They forgot all about me. They made a lot of money. But at that time, though, hip-hop music they called it oftentimes drop-in science. And oftentimes, a lot of rappers would actually speak about scientific concepts. They would make allusions to scientific concepts. And one of my favorites, and many people, including Eminem, claims this person is one of the greatest rappers of all time. Okay? That's a G-R-A-T. That's not GOAT. That's great. Anyway, this is Rakim. And so this is this song went #1. It kind of took over the planet at the time, and all the young people were looking up to him. And if you listen to that rhyme, it goes, that's what I'm saying. I drop science like a scientist. My melodies are cold the very next episode. Has the mic off in the store and ready to explode. I kick the mic at Fahrenheit, freeze MCs to make them colder. My listening system is kicking like solar. So rappers at that time, they would have hidden codes in their rhymes. It wouldn't be literal. So he's like rapping about a supernova explosion, an exploding star. And so as a young person, we looked up to the hip-hop artists as actually scientific minds. They would refer to going to the recording studios, going back to the lab, where they would explore and experiment and create and build new electronics, right, to make crossfaders and make turntables do what they do. So this was what science looked like to me when I was growing up. And another person that influenced me in terms of this conflict was Albert Einstein, because Einstein wore his personality on his sleeve. He didn't fit into the tropes that we think scientists should be. And when he got stuck in a problem, he would go on a piano and improvise away, even though he didn't know how to play it. He was a very good violinist. He was known for his sound, not his technique, and that's something we look up to in the jazz world. Dennis, would you agree?
I would agree.
The sound that's what it's about. And of course, many people know John Coltrane as probably one of the greatest musicians of the last century, period, regardless of the genre of music. But how many of us know that John Coltrane read everything about Albert Einstein that he can get his hands on? And he was trying to, he approached his music like a scientist and a mathematician. He was trying to find, him and Wayne Shorter, for example, they saw music not simply as a form of entertainment, but something that can change the world, that can change people's minds. They felt like they could bend the fabric of space-time with their sound and their music. And Coltrane was going after a system similar to what Albert Einstein did with symmetry and invariance, and this is his own handwriting. This is a diagram that he drew in trying to figure out this system. And we'll get back to this at the end of my talk, and might even play some of this. But I wish, the conflict that I had as a young person didn't have to be so, okay? It turns out that this is an age-old thing. I wish that my teachers would have told me that from the very birth of what we now call Western science, and even science from Africa, because Pythagoras spent about 18 years in Egypt, that they believed that actually the Pythagoreans believed in something called music of the spheres, that the planets played a harmony in proportion to the distance, okay, from the Earth. It was an Earth-centric universe back then. And in fact, the Pythagoreans created the word cosmos. That word came from the Pythagoreans, which referred to the order, that which has order in the universe and harmony. So what did Pythagoras do? So many of us, I see some young people in the audience, right? I'm going to call on somebody here. I see the young man there in the purple shirt there, okay? So Pythagoras, when I say Pythagoras, what's the first thing that comes to mind? That's right, the Pythagorean. Give the man a hand, young man a hand. All right. All right. I see a young lady there. You have a nice t-shirt that says, "Stay inspired." Okay, I love that. I love that. I'm going to remember that when I get back on my plane ride. Do you know, I'm going to ask you a question. Given that Pythagoras did the Pythagorean theorem, but he believed in music of the spheres, do you think that Pythagoras played around with music? Do you think that he would have wanted to do this? Okay, you're completely correct. Okay, that was a nice setup. So I'm now going to call up Dennis. We're going to do a little demonstration. This is an invention. Pythagoras, I won't get into the whole folklore and the story about how he made this discovery, what inspired him, but he basically had one of these, what do you call those moments, aha moments, and he said, aha, and he went to make this instrument called a monochord, and what you're looking at here is basically, a bridge that you have a string suspended, clipped at the end, and you could slide this bridge and then pluck the string. This is a modern version of a monochord, except he's using his finger to pluck the string. So the first thing we're going to do is play the lowest note on one of the strings, and just, okay, so that's this one here, that's this vibration. My question is, if I pluck half of the string, so the Pythagoreans believed in whole numbers were sacred, going up to the number 10. You would get assassinated, actually, if you work with irrational numbers and if you ate beans, okay? So 1/2 is the other perfect integer, sort of whole term. So play that. Does anybody recognize the difference between, or the similarity between the first one? Half. It's an octave. Okay, let's do a third. The other ratio. So just play them in sequence. Okay, that's a perfect fifth. That's we call it dominant. 1/4, please. So you see where this is going. Basically, the discovery of what we call the Western tonal system, right, was discovered by Pythagoras. And he discovered it from the intuition, right, this belief in music of the spheres. He was trying to make a replica of what he thought was going on out there in outer space with these ratios. So basically, the entire diatonic system. So let me show you something that's really cool. It's like, I noticed that Brian Eno was out here not too long ago, and he's really hip to this. He told me that. So watch this. I'm going to play something that the music experts should know about. That's a minor scale, right? But you know this one, right? I just played the same notes, all right? So all of the qualities, all of the different scales that we play with, diminish, all these scales are contained in what Pythagoras did, coming from the ratios. So that's an important thing because we're now going to see the development of modern. Thank you, Dennis. We'll get Dennis back in a second. Dennis has been teaching. Dennis is a great musician, not only because he has a good feel. He's been teaching the blind children music for like 33 years, right? We appreciate you. Right. But it didn't end there. People were still trying to understand the motion of the planets for like 2,000 years after roughly 500 BC when the Pythagoreans came on the scene. and his followers like Plato and Aristotle, they all these people whose name I still can't pronounce, okay? But here's the point. They were getting it all wrong. You probably heard about Copernicus and the sun-centered universe, right? Heliocentrism. But this person came on the scene in the early 1600s. He had an interesting life. You want a good read, understand somebody with a crazy life, is this guy. There's some rumor that he only took 3 showers in his life. I mean, wow, yeah. Anyway, I would love to wear one of those. So what we're looking at here was, he had these models that were based on Platonic solids, because Plato was one of his heroes. He tried to understand the motion of the planets using these geometric models, because this was coming from the Pythagoreans and Plato, and failed. And then he returned back to Pythagoras, the idea of music of the spheres. And what he did was, he had data from Tycho Brahe, this guy that got his nose cut off in a sword fight. He had a metal nose. I usually have that picture there. That's a good Halloween costume, I think, to wear. So what he did was, in trying to figure out, the motion of the planets, the underlying astrophysics, the first person to write down equations for astrophysics, okay, called Kepler's laws. And what you're looking up here is basically the idea now, or the fact, that planets are going around the sun with an elliptical orbit, and that all planets, most of them, unless it's like some perfect, perfect planet that's going around a circular thing, aside from that, he discovered it actually from this. This is his handwriting. Back then, astronomers or natural scientists were trained in music theory. And what he did was, he took just like how Pythagoras took the ratios of strings, he took the ratios with the belief that the planets were playing a harmony, like Pythagoras said. He took the ratios of the velocities of the planets, of a planet as it's moving slowest from the sun and fastest relative to the sun. And for example, the Earth had basically a perfect fifth, okay? So he really believed in this, and then he wrote down the notes, and then through that, he got to this. All right, so this idea of making parallels, okay, between music and astronomy and physics is nothing new. The question is, so, we use Kepler's laws to find gazillions of exoplanets outside of our solar system. That same law is being used by that satellite. All right, so what we're going to do now is develop. So I'm now going to get a little bit pedagogical here, okay? I mean, I got to do this. So what we're going to do now is kind of go through 3 things. I'm going to elucidate something about cosmology, right? The cosmology that we deal with today. And then from there, go into the quantum world. And in doing though, I'm going to use music. I'm going to use some of the language of music to, I hoped, to inspire, to clarify maybe, right? This type of physics. Because as humans, we do have a natural, I don't have to tell you anything about, I'm not going to play yet. I don't have to tell you anything about the ratios. When you hear a sound, you hear a sound, right? It's kind of embedded in us. So that's what I'm going to do moving forward, okay? So let's go on this journey together, and let's begin. Oh, I got to go back. So we just demonstrated that waves can come in these harmonic forms, meaning that we can understand certain types of sound waves. We call them standing waves because they appear to just be standing still. They're not really standing still, but just, the endpoints are usually fixed. They're really vibrating up and down, but these things we call nodes, they stand fixed. And this gives us basically the different tones, right? The different pitches that we hear. Do, re, mi, fa, sol, la, ti, do. All right? And These things are mechanically generated in instruments. So we're looking at here a flute, and we have the pressure waves, okay, of air molecules that's generating a wave pattern as I blow, as I blow through the flute, for example. But waves are actually much more interesting than that. These types of waves are called what we call simple harmonic waves because they're very periodic and simple. But they have a special property, which is when I add them together, as you're seeing here. And it's not important that you can actually predict how complicated it is. It's just important that you know that when I add simple waves, I get complicated waves. And the magic is, if I present to you, or a physicist or an astronomer, I present to them, or a computer scientist, a complicated wave, or engineer, they can decompose it into the simple waves. It's just like I could take a word and decompose it into the letters of an alphabet. And this is a very important technique. It's called the Fourier transform. And we use this. This is like one of the mother tools that we use in scientific research. And in fact, what we're going to now do is try to take what Kepler did for planets and apply that to the universe. Are you ready for this? Or not? Okay. You're like, could this guy just shut up and just play some music? Okay, so what we're looking at here is a computer simulation which matches the data really well of the large-scale distribution of what? So if you look at this, it looks like, the glimmering of lake waves on a lake on a bright lit moonlight evening, summer evening. But actually, it is the large-scale distributions of galaxies that we're looking at here. And if we zoom out, we basically see galaxies. And these days, we have measured on the order of 1 billion galaxies, our own Milky Way being one of those galaxies. And so this is a large-scale distribution of structure in our universe. And one of the big research projects actually happens here at the Perimeter Institute is to understand the physics that led to this, right? This is one of the holy grails of research. What is the physics that led to the formation of the galaxies? Well, what do we mean by that? Well, what we mean by that is a picture today, the here and now. And this is a picture of the universe at the largest distance scales that we can see, going back about 14 billion years ago. And in fact, by measuring the properties, this is a baby picture of the universe. It's called a cosmic microwave background radiation. And by measuring the properties of this, we discover it's actually, there are no galaxies, no nothing. It's just a seething, vibrating ocean of plasma, which is basically, a charged, something similar to the surface of the sun, okay? And it's waving with tiny little ripples. And we can compare the physics of this to later on and realize that a very interesting picture, that these tiny little undulations, tiny little waves, underwent gravitational collapse with some mysterious form of matter that we still don't know what it is. We call it dark matter, but we don't know what it really is. We know it exists because we need it to form those galaxies. And again, this is very, there are different subgroups within astrophysics and physics and cosmology that spend time studying the different epochs of how this happened. But what I want to do is to actually understand this through the lens of music. This is a nice little animation of how the early universe, that CMB, the cosmic microwave background, those undulations, how they can grow and develop into, this is a three-dimensional rendition of that data I showed you. Let's see if it works. You'll see it will start off with, and then eventually, this is a computer simulation that captures this physics. And to understand that, what we're going to do is look and study the physics of an instrument. So I'm going to call Dennis back. And Dennis is going to play for me an A, and I'm going to play an A. I was not going to do a blind test because you clearly will know it's a bass and you know this is a sax. So Dennis, play me an A. It's a good time for us to be in tune with each other, too. Okay? I'm going to play an A. Play an A. Okay, you all agree that's an A, right? Yeah, it sounds like A. But what makes a bass sound like a bass and a sax sound like a sax? Because if it was only just one vibration, right, doing that, then that would be it. But what we actually see going on when an instrument actually generates a note, one note, is that on the x-axis, every point here corresponds to one frequency, one vibration. And as I sweep across, it's like an equalizer. So actually, when an instrument plays, it generates a range of vibrations. This instrument is generating a whole set of vibrations, a spectrum of vibrations, but at different volumes or amplitude. And the one that you hear the most, the one that you hear as the A, is the loudest one. And these others, your brain perceives that as the timbre or the color or the saxophoneness or the bassness of the bass. It is the signature of what gives the instrument its personality. Okay, and that's very important. But what does that reveal? So this just represents the physical vibration of the instrument. It's gonna represent the material makeup of the instrument, the geometry and the shape of the instrument, right? And so we can actually look at this spectrum and by using this Fourier transform idea, decompose it and figure out what instrument we're playing, all right? And this is a very important thing when we do synthesis, when people do make synthesizers. That's basically the physics going on there. Thank you, Dennis. Oh, you want to? Dennis is a champ, that's what I can say. Yeah, I know, making him work here. Thank you. All right. So this is a very important piece of physics because we're going to use this idea that objects vibrate and they generate a whole set of vibrations, including instruments, and we see basically different resonances, okay, that reveal the geometry and the material makeup. So let's do the same thing for what appears to be this very chaotic cosmic microwave background radiation. We can decompose the waves of the universe that's vibrating in a similar way that we did for the instrument, can't we? We're allowed to do this. We're scientists, right? We can just decompose these waves, they look very complicated, and say how much of what frequency is contained and how loud is it for this thing, right? By the way, the different colors correspond to the different heights of those waves, roughly speaking. And if we do this, lo and behold, this is what we see. We actually see that the universe is functioning like a very simple instrument. The first peak corresponds to the loudest note, actually, which is actually the A note, believe it or not, many octaves lower. All right? The other peaks represent, if we believe in this hypothesis, should represent something about the geometry and the material makeup of the universe. And even back then, in the early 90s, we knew that there had to be dark matter in the universe because of this peak. Before even realizing that they existed, we kind of knew that already from Vera Rubin and Zwicky. But this already, looking at the early universe and how it vibrated, the material makeup of the universe is revealed by these other peaks. And that's basically the physics. That was the Canadian Jim Peebles Nobel Prize, right? That was his prediction. That red curve is his prediction that he did in the 70s, a best fit prediction. All right, now we're going to move into the quantum world. So we made a little parallel. We used a little bit of ideas of music and sound, right, to shed some light on the underlying physics behind the early universe and how structure could be formed. It's not the complete story, but the point is to find a pathway and then jump back and get more complicated if you want to get more complicated. Jazz it up a little bit more. And that's what we're going to do now. So when I was writing my book, The Jazz of Physics, back, 10 years ago, I got an email from, and I we all get emails from people, and it was from, oh, I have a quantum theory of music. I'm like, okay, junk box. The problem is, it was this person that wrote me the email. Okay, do y'all know who this guy is? You know who Miles Davis is? Okay, you know Art Blakey is? Okay, he played with those people, okay, and then some, right? New Orleans, Wynton Marsalis, yeah, this is the NEA jazz master, okay, Donald Harrison from New Orleans. It was him that sent me that email. Well, I had to go back and do some apologizing years later, and we continued talking. And in fact, in June the 22nd, we're going to be playing. We have a concert in Kansas City, the home place, birthplace of Charlie Parker. So what's his idea? Donald Harrison had an idea. Oh, let me tell you another thing. The reason why I get involved in the whole music science thing is because I just want to become a better musician, and I have to use whatever crutch I have. You know what I mean? Like, you know, right. So this is my in. This is how I get in to talk to the musicians. They want to talk to a physicist, right? So I'm like, hey, I'm available. I can talk quantum. Hey, what about that 251, man? So that's what's going on with me and Donald, right? So I tell him about my quantum stuff, and I can't believe this is happening to me. I'm like, you can't believe this is happening to me. I can't believe I'm talking to Donald Harrison, right? So what is this idea? So what Donald said to me, so by the way, Donald Harrison, if you are a sax player, and he is a living Charlie Parker, okay? His stuff is incredible. I mean, he could just play seamless through the chord. He's just so good. And I was like, how does he do this? So I said, Donald, how do you do it? He goes, well, I don't play the changes. I'm like, you don't play the changes? By the way, in jazz, we have chord changes that changed over time, and your job is to make sure you're playing within the changes. And if you're going to play outside the chord changes, it better sound hip. All right, so Donald Harrison, he goes, yeah, man, it's like quantum mechanics. I was like, what do you mean? He goes, I don't play in the changes, I play through the changes. I said, oh, let's talk more about this. And then after 3 years or something, we realized that actually this idea of a strategy for jazz improvisation, right? There are many strategies, many ways you can maybe artfully improvise through what have you in jazz, chord changes, rhythm changes, yada, yada, yada. But he had another strategy, and it lined up with how we think about quantum mechanics. So let's actually use jazz improvisation to understand a mystery about how to interpret quantum mechanics. Let's just do this. So in classical physics, if I throw Dennis's bass across the room, I won't do that. He gave me that look. If I threw a ball from point A to point B in a straight line, it's obviously going to do something very intuitively, right, straightforward. And what's it going to do? Well, let's say it's going to traverse a unique path. No matter how complicated that path is, it will be unique, given the initial condition. But what Richard Feynman taught us how to think about what quantum particles do, what quantum entities do, is that when they move from point A to point B, according to the equations that we have to trust to make all those devices that's going to come out of the PI, right? It has to traverse the one particle. I just draw through lines. Has to traverse every possible path from point A to point B. And that is completely bananas. Okay? If you really sit and think about this, and I'm looking at my friend, chair at Perimeter Institute, Laurent, who I've known for a while, you still puzzle about, don't you? Still drives you crazy? Don't admit that to people. I mean, all right, but the point here is that this is actually what it's saying. That's what the equations are saying. But there are people at PI who are paid to do something called foundations of quantum mechanics, and their job is to figure out the correct or the best interpretation. How do you interpret this? And so that's kind of what the game we're going to play now, is use Donald Harrison's idea of playing through the changes. So let's use this analogy. So we developed a theory. Okay. And the theory is very simple. So the idea is the same way a quantum particle starts off at a given position. So I want you to analogize a note as a particle. And it moves, then I could think of many notes, and then an endpoint. So if I go from, for example, the G to C, right, I might be able to do something like, that's one line. Or I could do something like, and all of these possibilities are sort of improvisations or considerations of a whole set of infinite possibilities as I go from point A to point B. So an improvised jazz line considers all possibilities. So the interpretation is quantum particles improvise their way from point A to point B. Okay? And that's kind of interesting there are some interpretations of quantum mechanics that actually say something close to that. So that's an interesting thing that's another kind of parallel, and we'll be playing some of that later on. We'll be applying some of these ideas. So part of what we're going to do, by the way, I'm going to kind of run through this talk so that we have time to actually play and demonstrate in real time some of these ideas. And so this is the path integral now for, this is kind of the picture. You're playing through the changes. You're not playing. So the point here is that, let me say it another way. As music is happening, it's happening too quickly for you to think about it if you're improvising. And the minute you stop to think, you may stumble and fall, right? So the point here is, what is the point? I know I was going to make a point here. Huh? That's right, yeah. So the point here is you have many different paths that you can start, and you're playing through the changes. So it really doesn't matter what path you might take. It's where you end and where you land. And that takes a lot of practice, by the way. It's not anyone can get up there and just do that. One has to practice the strategy. All right, so instead of thinking about, 251, dominant 7, that's not happening here. What you want to do is now internalize the beginning and end points of chord changes. And you want to practice that strategy. Okay, just like a gymnast is practicing and tripping and doing all these things, right? So that's kind of an interesting lesson. Another thing that's very important in physics, we talk about the macroscopic universe earlier on. We're moving into the microscopic. So in quantum mechanics, we have this many paths interpretation, but another important thing that guides quantum mechanics are symmetries. And this organization of different nuclear matter, governed by the strong interactions, a Nobel Prize was given to Mary Gell-Mann for figuring out the underlying eightfold symmetry. Okay, fancy word, the group SU3, right? Basically, colors the different types of nuclear matter states just governed by symmetry of that theory. And it's kind of interesting that one of the things that I've been playing with as a person that tries to use my music to inform my science, and that could just simply be listening to music while I'm doing my calculation, right? Or falling asleep. Because you never know, right? The idea may come in a dream. Or using physics to say something, to understand or clarify my music. And so one of the things I've been playing with a lot these days is these weird parallels. Like, look at that. That's the quantum chromodynamics. That's the strong interactions. I mean, it is one beautiful theory. It is just so spectacular. I know that Katie is still wondering about this. Still puzzling about this. Look at this one. This is the organization of the consonant tones. Basically, this is how, in tonal space, perfect fifths, fourths, and the diatonic system are organized. So this is the kind of stuff that I spend my time just like staring at, right? I know it's like uncanny, but that's kind of interesting. Now, it doesn't, I mean, one thing that you can say is that there are many musical systems and many cultures play da 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 da. That's not actually quite true. Most cultures, regardless of their musical system, recognize the perfect fifth, right? It is something that is actually sort of registered. I mean, the work of Carol Kremanskill at Cornell University, experimental psychology, we humans recognize the perfect fifth. And the minute you establish the dominant or this perfect fifth, and that's what we're looking at here, like if you go across and you project down this hexagonal system, these are all the perfect fifths. Like, the minute you do that, you have it. And I find it to be very interesting. You have this structure. And in that note, the journey continues. I've deliberately decided to make my talk shorter so that we can play for the rest of the time, unless you want me to continue talking. Show of hands. How many more people want me to talk or play with Dennis? Play with Dennis? All right, thank you. All right. So we're going to do three songs. We don't have a drummer, so Dennis has the hard work of both keeping rhythm and keeping time and keeping harmony, and I'm the one playing the fool up here at the horn. Okay. And so we're going to do two songs. One is a song written by one of my favorite sax players and a former teacher of mine, Joe Henderson. It's called Blue Bossa. It's kind of like a Brazilian-oriented bossa nova. The second song, you'll all know what it is. And the third song is something based on these symmetric scales. Okay? So, Blue Bossa. Let's get this. Huh? I'll let you start, and 1 second, let me just.
You want a note?
Yeah. Thank you. Okay, I need some water. Yeah, yep. I heard that some of us brought, from the SciComm crew here, we brought good weather with us, right? So it feels a little bit like summertime. So on that note, we just bring up the thing. Okay, we're gonna play this now. All right, so we're doing. Thank you very much. Thank you, Devin. Thank you, guys. All right. Okay.
Thank you so much, Stefan. Let's all thank Stefan Alexander one more time. And one more big round of applause for our bassist, Dennis Rondo.
Now, if you have questions for Professor Alexander, there is a microphone right there. So please make your way to the microphone.
questions whatsoever. Just don't tell me that, you didn't like the music, that's all.
We have one question that was submitted online. We could start with that one, maybe. Okay, so a question submitted online. Have you encountered scientists in other fields who have also discovered connections between music and their area of research, like biology or chemistry?
Yes, the answer is yes. I have a whole set of friends that are different types of scientists. In fact, I have many scientist friends that are musicians. So you have a friend that's a biologist that, looks at, she gets hip on the genetic code and the different sequences, and she likes to play them and compose to them. Yeah, so the answer is yes.
Our first question from the audience.
I can't believe that I actually understood you at the end, I think.
You mean the free jazz piece, right?
I was sitting there for a long time thinking, how can this be? And then my toes started tapping, and my hands started moving, my head started moving, and I began to see that the planets going around the sun, they can see the music of the sun, they can hear it, and they are drawn to it, to the music, just the same way I was. And I was like bopping. I wasn't trying to upset everybody near me, but I probably did. But
it's funny you say that, because when Kepler came up with his system, his imagination was that there was some divine being that was listening to the pleasure of the planets going around. That was, if you read his Musica, whatever this thing is, Harmonia Musica, his tome, that's the premise of it, that there was some celestial being at the middle of the sun enjoying the music of the planets. So you had to go figure it out.
it would be nice if you could figure it out. I don't know what the math will look like. Maybe just musical notes, who knows?
Or noise, just kidding. But some people like noise.
Yeah, sorry to bother you folks.
Thank you very much.
But I thought I should say that.
Thank you.
I just wanted to ask, what was it like when you were in school having to juggle both academics as well as music, since they can be two very different things?
Yeah, it's interesting because, I grew up thinking that music was this thing that the cool kids did, and then the science was the thing that nerds did. But then I discovered actually that the musicians were actually more nerds than the scientists in some respects. So I had to learn that. Yeah.
Thank you.
Thank you. That's a great question.
I just had a
But
question.
do both, okay?
When you showed us the diagram that was the 3D model of the notes all connected to one another, how are they connected? Like, is that showing like the wavelengths, the different?
Oh, say that
wavelengths
the
between them?
last part. I just didn't.
When you showed us the 3D diagram of all
Yes.
the notes connected, like how is that set up? Like, is it based on wavelength of the notes, or?
Very good. It is.
Okay.
That's right. So the distance is the relationship between the different frequencies in a given space. So there's something called, if you're interested, from Fred Lerdahl and Jackendorf, Ray Jackendorf wrote a book called Tonal Pitch Space, and it gets into all of that geometry.
Thanks.
Sure.
There's another person coming down.
Hey,
Hi.
I was just curious, like you wrote that song about like the circle of fifths and all that. Have you ever written any like songs about your research or like anything inspired by that?
Oh, I have a band. That's what we have a band. So there's a secret life I live. It's called, I have a band called God Particle with Melvin Gibbs and Will Calhoun and every now and Vernon Reed from time to time. And it's all original compositions. And these compositions are based on some of these concepts, but it has to be musical. So that's why I collaborate with them who know more music than me.
It's called Dark Particle?
God Particle.
God Particle.
Particle.
God Particle,
Yeah,
okay. Are you on
I know
Spotify?
it's a play on words. Yeah.
Is it on Spotify?
Huh?
Is it on Spotify or like YouTube or anything
If
like
you
that?
can, yeah, I think we have some live shows if you on YouTube, but we didn't really. I mean, we're kind of like the secret outfit kind of we play. Yeah.
Thanks.
Any other questions about cosmology, about jazz?
We can go to one more
Oh,
on.
there's a question over here. Should we,
Maybe we should bring a mic.
can we
to
bring a mic? We'll
Yeah, there's a mic
bring
right here.
We'll bring a mic. You can,
Yeah.
it's all right.
Okay. Speak into it and see if it works. Well, maybe you can ask the question and I can repeat it.
Yeah.
All right, so I'll repeat the question.
Okay, we're going to go to an online question, and then we're going to come back. We'll figure out the mic and.
I think he's,
Okay.
some noisy components, and those noisy components did you try to eliminate the profit of this instrument which was bought from company, from some producer?
Okay, so I think what I heard is that's correct. That when I played, I showed you a picture of the frequencies generated by the instrument. There's noise. There's actually a noisy part of that spectrum, right? And I think I'm going to infer from your question, what does one do with that, right? Or what is that the idea? That's the question. That's very good because this is at the heart of what great jazz is about. It's about making use of the noise as well. So if you listen to great players, when they develop their sound, not the notes they're playing, there's a lot of manipulation of the noisy component of the instrument. And we practice that. Yeah. Yeah, I agree with you, and that's a much longer conversation that we can have offline. Thank you. That's hours and hours of discussion. Thank you.
Okay, we'll go to an online question, I think. If you could play music with anyone, living or dead, who would you choose?
Whoa, that's a heavy, heavy question. First of all, most of those people I'd be too intimidated to play with. Right, that's the first thing. So we think about some of them, we're like, there's no way I'm going to be on stage with John Coltrane. I'd rather be listening to him, right? But in terms of, that's a good question. I would say Prince. I'd probably beat on some drums or something like that.
Another question?
Hi, you stated early in your talk that most of Western music was based on the Pythagorean division of the frequencies. What about other forms of music like Eastern or African?
Good, yeah. So again, because even in Western music and the way it's developed, right, into like rock music and jazz, right, the fact that we have tonal music, but there are all these other dimensions of music, including noise, including polyrhythms, which is so I was just focusing on the tonal aspects of music. But there's a whole nother discussion about, for example, the Carnatic music of India and the number theory involved in those rhythms, and it's deep. And yeah, so there's other things, other limbs to this conversation.
Thank you.
You're welcome.
Yeah, can you walk, just come around? Thank you.
I love questions, by the way, because I get to wing things,
So this conversation has been talking a lot about the physical relationship between certain notes and certain lengths of waves and their effect on their musical effect, that sort of thing. But what I'm asking here is that a lot of jazz music it transcends a person's psychology to a certain place where they can conceive of ideas in a musical framework. And do you find that there's a relationship between your scientific mind and the way that it is processing information? Do you find that the jazz playing of the music creates a state where you can create better in terms of mathematics and looking at the word in a mathematical model?
Thanks for asking that question, because the part 2 of my talk is that type of exploration. In fact, much of my book is about the parallels between how, for example, physicists actually do. You see, there's learning physics that you learn in school, but the doing of it, the discovery process, the intuitions and the mistakes made and all those things, and that process mirrors a lot of what we see going on in jazz. And that's kind of like that part. And going back to what you were saying, that state of not knowing, maybe, that state of, sometimes, as a flicker of time, you have the wrong thought, but that wrong thought takes you in a different direction. That wrong note takes you in a different direction, and you have to embrace it and move with it. So that you do find, I have found lots of parallels that I see my colleagues who are not jazz musicians, right? They don't know anything about jazz, maybe. But I see some of them, the way they do physics looks a lot like jazz.
Would you say intuition has a lot to do with
Oh,
that
big time,
process?
big time. And a lot of what we do is that type of, and also developing our own unique personalities and intuition. Not everyone does it the same way, right? Yeah, thanks for asking the question.
And this is the last question.
Good evening. Thank you so much for that amazing, amazing lecture. You showed a graph earlier that had, you said that this was an A note and it was the sound of the universe. I was wondering, do you have an idea of what the instrument would look like? Because you said every note that's played on an instrument
That's what it
has
looks
all
like.
This, yeah.
Well, it's not up anymore. I showed you that curve. That's what it looks like. I mean, back then, when those waves were generated,
But
that was the analogy I was making. Huh?
What would the instrument that created that note look like? Any ideas?
Well, again, this is where the analogy is going to break down. The whole game of, no, it's good. The whole game of analogy making, which is what we do, and in a lot of ways, mathematics is kind of analogizing the physical world in some ways. And then you describe it really well, then you might find infinity. You got to figure out what to do with that, right? But the point is that the analogy making, you come very close to the thing, but it will break down. And where it breaks down is where things get interesting. And that's where you need imagination. You need new ideas. So in this case, you ask exactly the right question. So that instrument, whatever it is, it's something going on with space-time and quantum mechanics. And we're still puzzled about that. There are many ideas at PI about what might be going on there, that instrument.
Wonderful, thank you.
You're welcome.
We'll have to stop there. Let's all thank Stefan again for this wonderful evening of music and science.
Thank you. Thank you.